You've seen rainbows your whole life, dozens of them, maybe hundreds, and you probably think you understand what you're looking at. Light goes into water, comes out as colors. You learned that in school. Simple, right? Wrong. That's not an explanation. That's a label. You've taken something extraordinary and slapped a name on it and walked away thinking you understood it. But you don't. Not really. Let me show you what I mean. Answer me this. Why does water split light into colors? You can't just say refraction. That's another label. Why does refraction happen? Why those specific colors? Why always red on top and violet on the bottom? Why that specific arc shape? Why not a straight line? Why not a square? And here's one that should bother you. Why can you never reach a rainbow? You can walk toward it for hours. It moves, it retreats, it stays exactly the same distance away. What kind of thing does that? Most people shrug. It's just how rainbows work. But that's not thinking. That's surrendering. You're looking at something that reveals the deepest secrets of what light actually is. The rainbow is performing a physics demonstration right there in the sky. It's showing you something profound about the nature of electromagnetic radiation, about how different frequencies interact with matter, about why the universe has color at all. And you think it's just pretty. Here's what I'm going to show you. The rainbow isn't simple. The rainbow is a window into the fundamental structure of reality. And once you see what's really happening, once you understand why that arc forms exactly where it does, and why those colors appear in that exact order, you'll never look at light the same way again. You'll realize you've been staring at one of nature's most elegant demonstrations your entire life without understanding what it was telling you. So let's actually understand it. Let's start with the thing you think you know, light. What is light? You probably have some vague notion. It's the stuff that comes from the sun, the stuff that lets you see. Maybe you've heard it's a wave or a particle, or somehow both. It travels fast, it bounces off mirrors, it makes things visible. But here's the thing, light isn't just light. Light is electromagnetic radiation, the exact same fundamental force that holds every atom in your body together, the same force you feel when two magnets push apart in your hands, that invisible resistance through empty space, that's electromagnetism. And light is that force, oscillating, propagating through the vacuum at 299,792,458 meters per second. Think about what that means. When you look at a rainbow, you're not seeing some separate phenomenon. You're seeing the electromagnetic force made visible. You're watching electric and magnetic fields oscillate together, traveling through space, interacting with water, and entering your eyes. The rainbow and the magnet are cousins. Same fundamental force, different manifestations. Now here's what nobody tells you. White light isn't pure. You think of white as simple, basic, the absence of color. Wrong. White light is chaos. It's a tangled mess of every visible frequency, all superimposed on top of each other. Red light at 700 nanometers, orange at 620, yellow, green, blue, violet, all of them, all at once, all mixed together into what your brain interprets as white. The rainbow doesn't create colors. The colors were already there, hidden, buried inside that white light all along. What the rainbow does is sort them, separate them, untangle the mess and lay each frequency out in order so you can see what was always present but invisible. Newton figured this out 350 years ago. He took a prism, passed white light through it, and watched the colors fan out. Then he did something brilliant. He took those separated colors and passed them through another prism. They recombined into white. The colors weren't being created. They weren't being added by the glass. They were being revealed, sorted, exposed. A raindrop does the same thing. Every raindrop in that storm is a tiny prism, a spherical laboratory performing the same experiment Newton did, revealing what white light has been hiding from you your entire life. So let's zoom in. Forget the sky for a moment. Forget the millions of raindrops. Focus on just one, a single spherical drop of water hanging in the air, maybe 2 millimeters across, a tiny perfect sphere suspended in front of you. Light hits it. A beam of white sunlight, that chaotic mix of every frequency, strikes the surface of this little water droplet. And something happens. The light enters the water. But here's the thing you need to understand. Light slows down when it enters water. In a vacuum, light travels at its maximum speed. In water, it travels at about 75% of that speed. Not a huge difference, but enough to change everything. Now ask yourself, what happens when something moving in a straight line suddenly slows down on one side before the other? It turns. Think about it. If you're pushing a shopping cart and one wheel hits sand while the other stays on concrete, the cart pivots. It bends toward the slow side. The same thing happens with light. When a beam of light hits water at an angle, the part that enters first slows down first. The rest of the wavefront is still traveling at full speed in air, so the whole wave pivots. It bends toward the slower medium. We call this refraction, but don't let the name fool you into thinking you've explained it. The word refraction is just a description of what happens. The Y is pure geometry. It's inevitable. It's what waves must do when they change speed at an angle. There's no choice involved. No magic, just mathematics made physical. So the light bends as it enters the raindrop. It's now traveling through water at a new angle, but it doesn't just pass through and exit. The drop is spherical. The light hits the back surface, and some of it reflects, bounces back. The curved inner surface acts like a mirror. The light turns around, heads back toward the front of the drop, and exits. And as it exits, crossing from water back into air, it bends again. Refraction on the way in, reflection at the back, refraction on the way out. 3 interactions, 1 tiny drop of water. This is where the rainbow is born. Now here's the part that should break your brain. Not all light slows down by the same amount in water. Red light slows down a little. Blue light slows down more. Violet slows down even more than blue. Each frequency, each color has its own specific speed in water, its own refractive index. They're all different. Not by much, we're talking tiny fractions of a percent, but enough. So when that white light enters the raindrop, when all those tangled frequencies hit the surface together, they don't all bend by the same angle. Red bends a little, orange bends slightly more, yellow, green, blue, violet. Each one pivots a bit more than the last. They start to separate, they fan out. The colors that were all superimposed, all hidden inside the white, begin to sort themselves by frequency. The raindrop is acting like a prism, but it's not just any prism. It's a spherical prism that also reflects the light internally before sending it back out. So the separation happens twice, once on entry, once on exit. The colors fan out, bounce off the back, fan out again. By the time they leave the drop, red light is traveling in a measurably different direction than violet light. The separation is real. The angles are precise. Red exits at about 42 degrees from the incoming sunlight direction. Violet exits at about 40 degrees. 2 degrees of difference. That's the entire rainbow. That tiny angular spread, repeated across millions of drops, paints that arc across the sky. But wait, why do different frequencies travel at different speeds in water? Why should blue light care more about water molecules than red light does? This isn't obvious. This isn't something you can derive from common sense. The answer lies in how light actually interacts with matter at the atomic level. When light passes through water, it's not just sailing through empty space. It's encountering electrons in water molecules. Those electrons respond to the oscillating electromagnetic field of the light. They wiggle. They absorb and re-emit the light. And how strongly they respond depends on the frequency. Blue light, with its higher frequency, interacts more strongly with those electrons. It gets delayed more, it slows down more, it bends more. This is quantum electrodynamics, the most precisely tested theory in all of physics, the same theory that describes how magnets work, how atoms hold together, how chemistry happens. The rainbow isn't just pretty. It's quantum mechanics made visible. Every time you see those colors spread across the sky, you're watching electrons in water molecules responding differently to different frequencies of electromagnetic radiation. The rabbit hole goes deep, and we're just getting started. Let's follow that light inside the drop. It's entered the water. It's bent toward the center. Now it's traveling through the interior of this tiny sphere, but it doesn't just sail out the other side. It hits the back wall. Here's what happens at that back surface. Some of the light does pass through and exit, but some of it bounces, reflects. The curved inner surface of the raindrop acts like a spherical mirror. The light hits it and turns around, heads back the way it came. This is total internal reflection, light trapped inside a medium, bouncing off the boundary instead of escaping. And this bounce is critical. Without it, there's no rainbow. The light would just pass through the drop and continue on its way. The reflection is what sends it back toward you. So now the light is traveling back through the drop, heading toward the front surface where it originally entered. And when it reaches that boundary, when it crosses from water back into air, it refracts again, bends again, separates again. The colors that already started fanning out on entry now fan out even more on exit. Red goes one way, violet goes another. The angular separation doubles. The sorting that started at the first surface completes at the second. Each color exits the raindrop at a specific angle relative to the incoming sunlight. Red light comes out at about 42 degrees. Violet at about 40 degrees. Orange, yellow, green, blue, they're all in between, each at their own precise angle. These numbers aren't arbitrary. They're not approximate. They're the inevitable result of the refractive index of water at each frequency combined with the geometry of a sphere. You could calculate them. Physicists have. The math predicts exactly what we observe. This is why rainbows look the way they do. Not magic, not chance. Geometry and physics conspiring across millions of water droplets to paint light across the sky. Now pull back. Stop thinking about one raindrop. Think about the sky full of them. Millions of drops, billions, each one doing exactly the same thing. Light enters, bends, reflects, bends again, exits at those specific angles. Every single drop is performing the same physics experiment simultaneously. But here's the thing that should stop you cold. You don't see all those drops. You don't see a wall of color. You see an arc, a specific curved band across the sky. Why? Because you only see color from drops at very specific positions. Think about what has to happen for light to reach your eye. Sunlight comes from behind you. It hits raindrops in front of you. The light bounces inside those drops and exits at 42 degrees for red, 40 degrees for violet. But that angle is measured from the original direction of the sunlight. So the only drops that can send red light into your eyes are the ones positioned at exactly 42 degrees from the line connecting your head to the sun. The only drops sending violet to your eyes are at 40 degrees. This means the red light you see comes from higher drops. The violet comes from lower drops. Each color you perceive comes from a completely different set of raindrops. The rainbow isn't painted on the sky. It's not a thing sitting out there at some location. It's a geometric relationship between the sun, the raindrops, and your eye. Change any one of those three, and the rainbow changes. This is why you can never reach a rainbow. You walk toward it. The geometry shifts. New drops enter the critical angles. Old drops leave. The rainbow stays the same distance away, always the same angular relationship to you and the sun. It's not retreating from you. It's not moving at all. It's an optical phenomenon that exists only in relation to where you're standing. Chase it forever. You'll never get closer. And here's the strangest part. The rainbow you see is yours alone. The person standing next to you sees a different rainbow, their own personal arc, defined by their own position, their own angle to the sun, their own set of contributing raindrops. You're both looking at the same sky. You're both seeing a rainbow. But they're not the same rainbow. They can't be. The geometry makes it impossible. Everyone gets their own. The rainbow is a private conversation between you, the sun, and a billion tiny spheres of water. And now you're starting to see what you've been missing all these years. Sometimes you see two rainbows, a bright one below, a fainter one above. And if you look carefully, you'll notice something strange. The colors are reversed. The primary rainbow has red on top, violet on the bottom. The secondary rainbow flips it. Violet on top, red below. Why? Because the light bounced twice. In the primary rainbow, light enters the drop, reflects once off the back, and exits. In the secondary rainbow, the light reflects twice inside the drop before escaping. That second bounce changes the geometry. The light exits at a different angle, about 51 degrees instead of 42. And the extra reflection flips the order of the colors. More bouncing means more bending means a different result. The secondary rainbow is always fainter because each reflection loses some light. Some escapes instead of bouncing. By the time it's reflected twice, there's less intensity left. But it's the same physics, same drop, same process. Just one more bounce. But here's where it gets truly strange. Sometimes, if conditions are right, you'll see extra bands, faint arcs of color inside the primary rainbow, alternating light and dark. These are called supernumerary arcs, and they cannot be explained by refraction alone. Refraction would give you clean separation. One red band, one orange band, not these ghostly repetitions. The supernumerary arcs are interference patterns. They're proof that light is a wave. Here's what's happening. Light rays entering the raindrop at slightly different points can exit at the same angle. They've taken slightly different paths through the drop, traveled slightly different distances. When they emerge, they overlap. And when waves overlap, they interfere. If two waves arrive in sync, peak matching peak, they reinforce each other, bright band. If they arrive out of sync, peak matching trough, they cancel, dark band. The supernumerary arcs are light waves constructively and destructively interfering with each other. The rainbow is performing wave mechanics right in front of your eyes. This is quantum behavior made visible, not in some laboratory, not in some particle accelerator, right there in the sky after a rainstorm. The rainbow is showing you that light doesn't just travel in straight lines like little bullets. It spreads, overlaps, interferes with itself. It's a wave, and you can see the proof every time those faint extra bands appear inside the primary arc. Now step back. Look at what you've actually learned. A rainbow is not just pretty. It's not just a thing that happens after rain. It's a demonstration. A physics lecture written in light across the sky. It proves white light contains all colors. Newton suspected this. The rainbow confirms it every time it appears. Those colors weren't added by the water. They were extracted, sorted, revealed. It proves light bends when it changes medium. The geometry of refraction, the mathematics of wavefronts changing speed, it's all there in that arc. Every rainbow is evidence that light slows down in water and bends as a result. It proves different frequencies interact differently with matter. Red bends less than blue. That's not arbitrary, that's quantum electrodynamics. That's electrons in water molecules responding to electromagnetic waves, each frequency getting a different response. It proves light is a wave. The supernumerary arcs, those interference patterns, can't exist if light is just particles flying in straight lines. Only waves interfere. Only waves create those ghostly bands. The rainbow settles debates that raged for centuries, and it proves something deeper. It proves the universe is comprehensible, that the same laws governing atoms and electrons and electromagnetic fields also govern the light in the sky, that mathematics describes reality, that patterns repeat at every scale. Newton used rainbows to understand light itself. He saw what everyone had seen for millennia and asked, why? Really why? And in answering, he unlocked the nature of color, the structure of the spectrum, the behavior of light in matter. The rainbow was his laboratory, and every time you see one, you're seeing the electromagnetic spectrum made visible. You're watching the universe perform a demonstration of wave optics, quantum interactions, geometric inevitability. The rainbow doesn't need explaining away. It doesn't need reducing to something simpler so you can stop thinking about it. It needs appreciating for what it is, a window into how reality actually works. Not magic, something better, truth. If this changed how you see rainbows, imagine what else you're missing. Subscribe to Feynman Physics. Every video on this channel is designed to show you what's really happening beneath the surface of things you thought you understood. Electricity, gravity, light, time. The deeper you look, the more magnificent it becomes. Subscribing helps keep this channel alive. It tells the algorithm that this kind of content matters, that people want depth, not just entertainment. That understanding is worth pursuing. So hit subscribe, turn on notifications, and let's keep exploring together, because the universe is stranger and more beautiful than you ever imagined. And we've only just started.